What's up, y'all? Welcome to a video on vectors, vector addition, vector subtraction, and vector component manipulation. This is a really important concept since vectors are the tool that we use for storing and manipulating information in physics. Also, make sure you download those follow along fill-in-the-blank notes linked in the description so you can make sure you don't have to write down every word I say and that what you learn in this video sticks for later. Now let's get to the chalkboard. All right. So, as you may have heard countless times, or maybe hearing for the first time, totally okay too, but vectors have both magnitude and they have direction. These are the two components of information that they carry. So now the typical example of this is speed versus velocity. So let's look at, let's say, a car. This is a car right here. And let's say it has a speed of 60 kilometers per hour. Well, so we know how fast it is going, but we don't know what direction it's going. It could be going north, east, south, or west. And I'll just label that. Now, the 60 kilometers per hour, that's actually the magnitude of some velocity, given that we know it's moving in some direction. So now let's draw another car. And this one is moving with a velocity of 60 kilometers per hour east. And so here we have information about both its magnitude, its speed, and its direction. Now in physics, we typically don't use north, east, south, or west to describe something. Instead, we introduce a right-handed coordinate system with unit vectors I hat, j hat, and k hat, and I'll get into that a bit more later. Okay, so how do we add vectors? Well, I'll start with the sort of algorithmic procedure to show you how we do this geometrically without any motivation, but then once we've got through that, I'll give you the motivation for why that sort of works, and then once we've gotten through that, I'll show you how you do them algebraically, which is how you'll most commonly be doing it in physics. So just bear with me for a second and we'll get straight through this. All right, so I want to now run through the algorithmic procedure to add the vectors geometrically. So this is called the tail to tip method. And what we do is we have these two vectors, A and B, and then and we want to add them with the tail to tip method. So let's think about what a tail and tip is. So if we have some sort of arbitrary vector here, this is any vector, then this end without the arrow is called the tail, and this end that has the arrow is called the tip. So now let's see if we can follow these steps to just add find the sum, a plus b. So here I'll just circle this, that's the tip, and that's the tail, and we want to find a plus b. Okay, so it says connect the tail of b to the tip of a. So let's redraw a, and here's its tail, here's its tail, here's its tip. And so we want to connect the tail of b, so that'd be this part right here, to the tip of a, that right here. So I'm keeping b in the totally same shape and direction, and now I have connected its tail to the tip of a. Okay, so that's the first step. So now let me redraw that on this side right here. Let's follow what this next step is. This next step says to connect the remaining tail to tip, and then it says tip tip. So basically what we want to do here is we see that we have a tail right here and a tip left right here, and we want to connect those two somehow. But remember, vectors have directions, so the way we connect them is important. And we want to follow this tip-tip thing where we bring these two tips next to each other like that. So this might sound a bit confusing so far, but I'm going to show you another method and we'll look at some examples, and I promise we'll clear up. So here's another very valid way of doing things. This is the parallelogram method. And so we have the same vectors, a plus b, and I'll just show you how we do it. So we want to bring a and b together, and then we make a parallelogram with that and take the diagonal. So this will be more clear when I actually do it. So first step, bring a and b together. So the way we're going to bring them together is with the same sort of tail to tip idea. So here's a, here's b. Okay, make a parallelogram. That's the first part of step 2. The way we want to make a parallelogram is just take this b and sort of make a copy of it, like we're doing Control-C, and then paste it down here. Okay? And then you can see if we just copy this A and paste it out here, we get this right here. So now what we have a perfect parallelogram, and we just want to take the diagonal of that. Okay, here's the diagonal. That's the diagonal, right? And then, so we sort of follow our tail to tip intuition, and we bring tips to tips. And this vector right here, this is the sum A plus B. So I'll redraw this right here. This is A plus B. That is the parallelogram method. Let's do a few examples now. Alrighty, so here we have two pretty simple examples of vector addition, and I'm going to do them with both the tail to tip method and the parallelogram method. So here's number 1, and here's 2. Okay, so for number 1, so we already have them brought together in tails and tips, so we can actually very easily connect the remaining tail to the remaining tip, and then we remember we want to bring tip and tip together, so that is actually A plus B. And we can also do this by the parallelogram method. So here I'm redrawing it, so I'm bringing A, and that's B. And now let me Control C B and Control V it down here. And let's do the same for A, but over here. And now we have a perfect parallelogram. We simply take the diagonal of this, and that's A plus B. And we notice our vector here looks very similar. It's actually the same as our vector here. That means either method works. So let's come over to the second example. Here they're not in tail to tip format yet, so we're going to have to redraw that. So let me draw A. That's approximately A. And here's B. So now I want to bring the tail of B to the tip of A. So let's go ahead and do that. So here's A, and here's B. This is A, this is B. And now I have a remaining tail and a remaining tip. What do? Connect them together. And then I know my rule, it's tip to tip. So we connect that, and this is A plus B. And we can also do this by creating a parallelogram. So let's just move this up a bit here. Okay, and so I'll just create my parallelogram up here. So let me Control C A and Control V it right here. And let's Control C B and Control V it right here. Copy paste. All right, now we take the diagonal of this, and we see that we have brought our tip together. And this is our sum, A plus B. And once again, these two look very similar, and that's because they are the same and both methods work. All right, so here we have a somewhat more complicated example. We have 4 vectors that we want to add, A plus B plus C plus D. So the way I'm going to approach this is I'm just going to take it one at a time. First I'm going to do A plus B, then I'm going to do that plus whatever plus C, and then I'm going to do whatever that is, A plus B plus C plus D. And that will give us our final answer. So let's get started. So here we have A, and I'm doing tail to tip method, so bring the tail of B to the tip of A. So now we have A and B, and now I see a tail and a tip that I can connect. Bring my tip to tip, that's A plus B. Cool. So I have this, now I want to do A plus B plus C. So let's copy A plus B over here, and we see that C looks something like this. So let's bring C down there. This is C, this is this A plus B, and I've brought the tip of, the tail of C to the tip of A plus B, and now I see a tail and a tip that I can connect, and let's go ahead and do that. And this is A plus B plus C. And I'm running out of board space, so let's remember what this looks like. This is just a horizontal line, and then we'll add it to D. Okay, so we had that A plus B plus C. looks something like that. And now let's bring in D. D looks something like this. And so here you see I brought the tail of D to the tip of A. I see a tail and a tip, and I connect them together. And there we go. This is our answer for A plus B plus C plus D. That's it. And you'll notice that I took this one step at a time, but I could have also gone a little bit faster. I could have drawn all the vectors together. So how would I do that? I would start here with A, then I'd bring the tip of B to the tail of A. So this is A. We've got a tip and a tail connected. This is B. Now let's bring in C. So let's bring the tip of C into the tail of C into the tip of A. And same thing for D. Here's D's tail connected to the tip of A. And I could go through the process like this. You see here I connect, this is A plus B. Let me make it a dotted line since it's part of the process. This is A plus B. Now I'm doing A plus B plus C. I see a tail and a tip here that I can connect and use my tip-tip rule. That was not good. So there we go. This is A plus B plus C. And then final step, A plus B plus C plus D. There it is. And you'll notice that these two are more or less the same. So that's a faster way to do it. Okay, so now let's take a look at an example that has A minus B. And so this is actually something that's vector subtraction. But don't be intimidated by these new vocabulary words. This is actually it follows very easily from vector addition. Because if we have A minus B, that's actually the same thing as A plus negative B. So the question is, what is negative B? Well, the way I get negative B is just by flipping the tip and the tail of B. So this is just B that I want to subtract from A. Well, negative B, I just flip the tip and the tail. So it's like that. So this is negative B. So now, let's see if I can add this A to this negative B. Well, that's pretty easy. I just take this A, and now I bring the the tail of negative B to the tip of A. Let me label that. That's A. And I see a tail and a tip that need connecting. This is negative B. And so I'll connect them. And this is A minus B. And once again, of course, I connected tip to tip, and that got me the answer. Okay, so I want to talk a little bit about the motivation for this and why this sort of works, this procedure of this tail to tip method giving us the sum of vectors. So let's do an example, sort of conceptual example. So this is a map of the United States of America. It's a beautiful drawing, by the way. And we want to talk a little bit about temperatures and their geography. So right down here we have Florida, and it's really, really warm in Florida, as usual. And up here we have Maine. Maine is in the north. You know, it's really cold up here in Maine. You go more north, you get to Canada and whatnot, it gets really cold. Okay, so let's represent that. So up here, this is cold, and this down here is warm. Okay, and I'm going to represent this with a vector actually, and my vector is going to go from cold to warm. That's not that great. Here we go. Cold to warm. All right. Now, for the purpose of this example, I'm going to assume something that's geographically inaccurate, but it will help us understand. So I'm going to say it's really cold, it's really warm down here in Florida, but for whatever reason, you know, in the Southwest here in Southern California, for some reason it's cold there, okay? And we say that as we go from east to west down here, it gets colder. Okay, well, let's draw a vector to represent that. So this is by no means geographically accurate. that's fine. But we can sort of from this discern the general trend in the temperature of the United States with these conditions. And you might be able to tell if you look at this map and think about it, that as you go down this way, it gets warmer in the United States. And so how do we think about that in terms of vectors? Well, let's add these two vectors. So I'm going to draw this vector up here using the tail to tip method. And so now we have a tail to a tip, and we have another tail and a tip, and I want to connect them, bringing tip to tip. There we go. And you see that the sum vector, the sum of these two vectors, is the exact general trend that we predicted. As we go down here, it gets warm, so that sort of gives you the idea of the sum of vectors. And the idea of the sum of the vectors being a sort of general trend can be generalized to examples in physics. So let's say we have an object and it has two components of velocity, one going this direction and another going this direction. Well, its overall trend velocity it will follow this path. And that's the sum of these two vectors using the tail to tip method. Another example, these could also be forces, for example. If this was some sort of force, and this is the x component of some force, and this is the y component of some force, then the overall force will be that general trend that's the sum of two vectors. That's sort of what we want to get at here. Okay, now it's time to introduce the algebraic tools that will allow us to use these vectors. So any vector is a vector in space, which for our purposes is an XYZ coordinate system. Okay, so we can resolve any vector in space into three components. And those components are each projections onto each axis. So here's the three components, each a component on each axis. And another way to write this is using our I hat, j hat, k hat conventions. Where I hat represents the x-axis, j hat represents the y-axis, and k hat represents the z-axis, components in each of those directions. Now to add two vectors, it's pretty simple. All you do is add the components. So if b is equal to b1, b2, and b3, then a plus b will just be a1 plus b1, a2 plus b2, and a3 plus b3. This is best illustrated by example, so let's do a few of those. Okay, so here's our first example. We'll work in this bracket notation. Okay, 3, 2 plus 1, 3. And I'll draw it this time because we're only in 2 dimensions. So here's my x-axis, here's my y-axis, and my vector 3, 2. That's 3 on x and 2 on y. And my vector 1, 3, that's 1 on x and 3 on y. So it goes something like this. And you can probably tell from using the tail to tip method or the parallelogram method, if I translate this here, now I've brought tail to tip, and then I connect, our result is going to look something like that. But all you have to do is just add the components. So let's add the source resultant sum vector. So its x component will be the sum of these two x components, 3 plus 1 is 4. And its y component will be the sum of these two y components, 2 plus 3 is 5. And that's your answer. Okay, so now we have an example in I hat and j hat coordinates. Recall that I hat is just x components, j hat is y components. So let's draw this out. This is the x direction, This is the y direction. And so I have negative 5 I hats, so that's 1, 2, 3, 4, 5 in the x direction. And I have 3 j hats, so that's 1, 2, 3 in the y direction. So our vector looks something like that. And I have 2 I hat, so that's 2 in the x direction, minus 1 j hat, that's negative 1 in the y direction. So we get something like that. Now let's add these two together. So adding the x components together, the I hat components, negative 5 plus 2 is negative 3 I hat. 3 minus 1 is 2 j hat. And that's our resultant vector. All right, let's do a subtraction example. So let's say I have 2 I hat plus j hat minus 0 I hat plus j hat. And we want the I hat component and the j hat component. Cool. Okay, so let's draw this out. Here's my x, here's my y. So my first vector, 2 I hat, 2 in the x direction or I hat direction, plus 1 j hat, 1 in that y direction, something like that. And my second vector is 0 I hat, so we're not moving in the x direction, and then it is plus 1 j hat, so it's something like that. And we actually want to take this vector away, so we want to flip its tail and its tip, and I've translated over here, so you can tell by vector addition that the sum will look something like that. You see I brought the tail to the tip, connected these, the sum will look something like that. And let's do the subtraction. So that's 2 I hat minus 0 I hat, that's 2 I hat, and then j hat minus j hat is just 0 j hat. And that's exactly what this vector right here is. So here's a three-dimensional example. We have I hat plus 2 j hat plus 3 k hat. K hat is the z component. And we want to add to that some 2 I hat plus 3 j hat plus 4 k hat. Before, all our k hat components have been 0, but now we're going to have to find them. So we need an I hat component, we need a j hat component, and we need a k hat component. Cool. So it's actually pretty difficult to visualize things from here. So I mean, I could draw a three-dimensional right-handed coordinate system. It would look something like, I mean, if I go 1 in the I hat direction, 2 in the j hat direction, and 3 in the k hat direction. You see it's a bit difficult to draw. I'm not exactly sure how I would draw that, so it would be something like that. Anyways, but we know we can just directly add components to get the sum. So 1 I hat plus 2 I hat is 3 I hat. 2 j hat plus 3 j hat is 5 j hat. And 3 k hat plus 4 k hat is 7 k hat. And that's our sum. The last part about a vector we need to address is magnitude. And magnitude is almost just like the size of a vector. So if you have a displacement vector, how large is it? Well, magnitude will tell you. If you have a velocity vector, how fast is it? The magnitude will tell you. If you have a force vector, you want to know how much force do you have? Magnitude will tell you. And so for a vector, v is equal to, with components v1, v2, and v3, the magnitude is simply obtained by adding all the components in quadrature, sort of like a Pythagorean theorem thing. So this is how we write the magnitude, and it is the square root of v1 squared plus v2 squared plus v3 squared. So that's just each component added together in quadrature. That's how we get the magnitude. Okay, so let's do a few examples. So, first example is, here's our vector, 3i hat plus 4j hat, and this is equal to v, and we want to find the magnitude. Well, this is some component v1, or I'll call it Vx actually. This is some component Vy. The magnitude, we know, is equal to the square root of Vx squared plus Vy squared plus Vz squared. But here, Vz is actually equal to 0. We have no k hat term. So we can solve this. 3 squared plus 4 squared. Well, that's one of your Pythagorean identities. You know this is actually equal to 5. Let's do another example. So we have, let's say we have negative 3i hat plus 2j hat. That's equal to some vector v. We want the magnitude. Magnitude of v is the square root of its x component squared plus y component squared. That should be out here. And we know there's no z component, so we could simply do this as negative 3 squared plus 2 squared, and that's just 9, that's 4, so this is just a square root of 13. So notice how the sign on this I hat component, which gives it a direction in the negative I hat direction, that has no impact on the magnitude because that goes away with the square. Last example, just in 3 dimensions. So let's do 3i hat plus 5j hat plus 7k hat. That's equal to our vector v. And I'm going to write down that's not the magnitude, that's just the vector. And our formula for magnitude is that it's the square root of the x component squared plus the y component squared plus the z component squared. We see we have a z component here, so we can't just say that's 0. That's 3 squared, that's 5 squared, that's 7 squared. So this is actually 9 plus 25 plus 49. You can work that out, and that is actually the square root of 83. And so that's the size of this vector. So that's what I got on vectors and vector addition. I recommend that you take 1 minute, just 1 minute, to pause the video and recall the following terms and concepts we covered in less than 1 sentence each. So pause the video and go! Okay, let's be honest, half of you didn't do that. But that's okay, because the best way to learn is to practice. Now, if you did that, that's great, but I need you to practice, practice, practice. So keep doing lots of practice problems, and I'll be back with another video ASAP on dot product and vector projections. See you then.